Welcome to The Explainer. Today, we're diving into the magic behind, well, basically our entire modern world, the semiconductor. It's the little piece of material that powers your phone, your car, your computer, but how does it actually work? How does a solid rock become the brain of a machine?
Okay, so we all know a light switch, right? You physically move something to let electricity flow or to stop it. Simple. But its modern-day cousin, the transistor, is on a whole other level. And the real game changer is that both its input and its output are electrical. This means the output of one tiny transistor can control the input of another, which can control another and another, all with zero moving parts.
And that little trick is what lets us build these vast, mind-bogglingly complex networks of transistors that make up a computer chip. But hold on. How on earth can a solid piece of material act like a switch? How can you tell it to change its conductivity just by, well, telling it to? Let's dig in.
So here's our game plan. We're going to build this thing from the ground up. First, we'll look at what makes semiconductors so special. Then we're going to shrink down and look at the weird quantum rules for a single electron. After that, we'll see what happens when you cram billions of atoms together. And finally, we'll see how that structure lets us build the perfect electrical switch.
All right, first up, let's talk about the core property that makes these things tick. Because honestly, it's not what most people think it is. Yeah, it's true. Their conductivity is somewhere between, say, copper and rubber. But that just means they're not a great conductor or a great insulator. The real superpower isn't where they sit on that spectrum. It's their ability to change. It's that they can be switched from acting like an insulator to acting like a conductor. That ability to flip states, that's everything. To really get a grip on how this switching works, we've got to shrink down, way, way down to the atomic level. We need to learn the strange and totally non-negotiable rules that electrons have to play by.
You know, in our big, everyday world, we'd imagine an electron's energy like a marble rolling in a smooth bowl. It can have any amount of energy depending on how high up the side it is. But the quantum world says, nope, not so fast. It's not a smooth bowl. It's more like a ladder. An electron can only stand on specific rungs.
And for our story, there are two rules that are absolutely critical. First, as we said, energy is quantized. Electrons can only exist on those specific rungs of the ladder, never ever in between. And second is something called the Pauli exclusion principle. It basically says you can only fit two electrons on any one rung, and they have to have opposite quantum spins. Think of it as one pointing up, one pointing down.
Okay, so that's the deal for one single lonely atom. But things get really wild when we take these individual atoms and their little energy ladders and squish them all together to form a solid. Now, you might think their energy levels would just merge, but they can't. Remember the Pauli exclusion principle? If two identical energy rungs merged into one, you'd suddenly have to kick out half the electrons to obey the two per rung rule. And physics hates that. It would create a super unstable situation. So the universe has this really clever workaround called energy level splitting. Instead of merging, the two levels actually split into two new ones, one with slightly less energy and one with slightly more. The total number of available spots for electrons stays the same, and the laws of physics are happy again.
And this splitting thing, it happens for every single atom you add to the party. So when you have billions upon billions of atoms packed together in a crystal, you get billions of these tiny splits. The individual energy levels get packed so incredibly close together that they stop looking like separate rungs on a ladder and start looking like wide, continuous bands of allowed energy. And this whole concept of energy bands, this is it. This is the secret sauce. It's what fundamentally defines the difference between a conductor, an insulator, and our semiconductor. It's not about the atoms themselves, but all about how these bands are filled up with electrons. So think of it like this. In a conductor, the top energy band is like a highway that's only half full. There are plenty of empty spots, so electrons can just zip around freely. In an insulator, that top band is completely full, bumper-to-bumper traffic. And the next empty band is miles away, over a huge mountain. Nobody's going anywhere. But in a semiconductor, the top band is also full, but the next empty band is just over a very, very small hill. In that space between the bands, that forbidden zone where no electrons can exist, that's the band gap. And I'm telling you, this little gap is probably the single most important feature in all of modern technology. That small, crossable gap is the key to absolutely everything. So, the big question, how do we actually use this tiny band gap to create our electrical switch? Well, this is where it all comes together. Let's close the loop.
Right, so at normal room temperature, just because of heat, a few of the most energetic electrons have enough of a kick to jump that small gap, that small hill. What a transistor does is, well, it's genius. It applies an electric field, that's our input voltage, which effectively lowers the height of the hill. The electrons themselves don't get any more energy, but the jump they have to make suddenly becomes much, much easier. So a tiny little change in that input voltage can drastically lower the barrier, and suddenly a massive flood of electrons can just pour across the gap. The material instantly snaps from behaving like an insulator to behaving like a conductor. And that's it. That's the switch. That is the transistor in action.
So you see, the whole point is that by understanding and, more importantly, manipulating these fundamental quantum rules, we've basically engineered a way to precisely control the flow of electrons on a massive scale. So what's the big takeaway from all this? It's that the ability to electrically control that tiny, tiny energy gap, that is the absolute foundation of all modern electronics, from the little LED in your remote to the most powerful supercomputer on Earth.